So domestic hot water, just like it says up there. And that starts about now-ish, in a minute.
That's mine. Very good. I need 1 second, Jens.
Yeah. What's that? See, Ragnar listens. I don't. You know each other, right? Ragnar, my wife?
I do.
Okay. I have totally forgotten about it.
Yeah, I saw her and your daughters out there.
Now, high temp is what you changed?
Huh?
Not down, talking John. Get a hot mic.
All right, who's ever talking, podium, thing up there. We don't want pictures the wrong way.
John?
Coming. Sure. Okay. So good. Very good. So good afternoon, everybody. Hello, hello, hello. How we talk? It is, but it's not very loud. Can you guys hear me? No. Okay. Okay, I try to speak a little louder. My name is Jens Ponikau. I'm the principal of Buffalo Geothermal, but I'm also the president of NY-GEO here. I want to welcome you. My talk is tonight, a little bit more of an introduction, so this is why I stepped back this morning, but thanks all for coming. It's a super pleasure to introduce Hugh Henderson. If you don't know him, you missed something, because he has the ears and eyes sometimes of NY-SODA. He works as a third-party verifier for them, or a monitor, so we've done multiple monitoring projects with him, and he was outstanding in drafting the reports for NY-SODA. That's what you see published on their website. He monitored both upstate and downstate the residential systems for NY-SODA. So he's the guardian of reality, how I call him. And so without further introduction, I asked him to go first on this project because he tells a little bit about what we did and how he monitored it. And then I talk a little bit more about how this all happened and what is a little bit of the innovation here. Very good. Thank you, Hugh.
Thanks, Jens. Yeah, I'm just about the facts, that's right. Okay, thanks for being here. And so at the top job competition, this project had been mentioned, and and there was a great presentation. And it's really kind of a neat project where a ground source heat pump was used to meet the domestic water heating load in a whole bunch of multifamily buildings. And it was really the first time, I think Jens had mentioned, it's the first time that's happened that just addressed the domestic hot water loads. And I want to focus on a certain aspect. It turns out that the way a DHW or domestic water system is arranged is really important. So I wanted to focus on some of the measurements that we did around that. And again, so this was NY-GEO hired a contractor, and down front Mark and Merrick were the contractors who took this on as a performance contract and met all the needs. And they put these ground source heat pump systems in 17 multifamily buildings, and Jens's company was involved. And like we said, it was the top job, one of the top jobs presenting this morning, and really putting the domestic water heating only on a geothermal system. It seems like you're missing something, the space heating load, of course. But it's a lot more expensive to address the space heating load and would have been a whole nother magnitude of project. And the other kind of key advantage of doing this, and Jens will talk about this more, is there's facility boilers in multifamily buildings that run at an extremely low level all summer long. With this system, you can shut the boilers down for 6 months, and there's just tremendous savings from just shutting a boiler down. For a boiler just to sit there and stay hot or idle or with the shutdown losses it consumes a whole bunch of gas, and doing this gets rid of that. And what I did, I came in the fall in September of 2024 and really did a one-day measurement and verification effort, and then we further got some data, and I was able to kind of compare these two systems and two arrangements. So there were two, so these buildings, we haven't heard, I just kind of throw this up to show that the buildings are, kind of similar, but not 100% identical. So we don't know exactly what the hot water use differences might be between the buildings, but they're on the same order. And so I wasn't able to address that. I'll just point out if, I like to measure things, and, a $1,000 cold water meter on the right spot could have told you just about everything. So, people who spend millions of dollars on the system, maybe just go by, and it can be connected to the BMS, that's nice, or just go buy one of the cheap ones at Granger and put it in. So anyway, I like to measure stuff, and of course I only get involved at the end, but I would have measured the hot water consumption on the cold water side, and then we would have known a lot more. So there's two systems, and they both had the same basket of parts, right? They both had a ground loop heat exchanger, and the source side pumping was similar. Okay. Oh, we're losing it? Yeah, I'll just keep going. So they both had 3 500-gallon preheating tanks, and they had a Finnish electrical tank that did the final heating on the hot water, and all those parts were the same. What was different between East Chester and Jackson was the arrangement of the system and the flow on the load side of the heat pump. So at Jackson, the three tanks, preheating tanks, were in parallel, meaning cold water came in the bottom of each, and I'll show you this, and it goes out, and that's kind of the traditional way to do it. And the recirc line that recircs hot water back to the tank came in on the cold water inlet to all the tanks. On East Chester, the tanks were in series, and the recirc line came back into the bottom of tank 2, and so that was the change. And the other, on the flow side, at Jackson, it had a traditional multi-pass heat pump arrangement, a 10 or a 15 degree temperature rise on the load side, where it was much higher temperature rise and lower flow for East Chester. And Buffalo Geothermal and the contractor had come up with this arrangement and wanted to test it. Okay, so Jackson, so showing it here, where the pointer is, I think I'll just, so the tanks on the bottom, again, you can see the cold water. The cold water comes into the bottom of each tank. Did my pointer do it?
No.
And so, so what do you think? Should we, there it is, okay. So the cold water, it is me. So the cold water comes on the tank, and then the hot water goes out. And so this is fun. And so in this arrangement, so the problem with this arrangement is the water entering the heat pumps is 110, 115 degrees. And so the heat pump has to work, and so the heat pump is less efficient when the load side temperature is, and then it gets heated up to 135. Okay, I'm gonna try to hit it carefully. On Eastchester, the tanks were in series, and so this shows, so cold water comes into the bottom of the first tank, it's blue, and then it goes out of the top of tank 1. I'll just keep talking, hope it comes back. And so it subsequently flows to the 2 tanks, and then the recirc line, as I said, the pink or purple line comes into the bottom of the second tank. And so we wanted to look at the differences between these 2 arrangements. And of course, in this case, the water coming into the heat pump, instead of being 110 degrees, is now 60 or 70 degrees. It's close to the city water temperature. And so to state the obvious in this thing, when the heat pump runs, now you're actually forcing water from the third tank. Hot water goes to the third tank, and then as you make more water, it pushes the hot water back through into the second tank and back into the first. When the first tank gets hot, it shuts off. And like Jens likes to call this cold water storage, which I think is the other way of saying it, is that, but really the key thing is you keep it stratified, right? So the enemy of a domestic hot water system is to mix all the water together. You want to stratify things as much as possible, and this does it. Okay, so the novel thing that Buffalo Geothermal and Adams European Contracting came up with was to find a way to have a high delta T, a high temperature difference, because if you're going to have cold water coming into the heat pump, you want it's going to come in at 60, but you want it to come out at 135. So that's a high delta T, and to do that, you have to have low flow through the heat pump. And the manufacturer, I think, is probably the room, but was not 100% enthusiastic about this because it's hard to control the heat pump. And the heat pump, there's John, and the heat pump can lock out on high pressure and things like that. So to make a multi-pass heat pump into a single-pass heat pump is a pretty difficult thing to do, and it takes controls that can respond really fast. And really not so HVAC control. Everybody thinks HVAC controls are fast. They're actually kind of slow and dumb. There are controllers that can be much faster, and it really took something faster than an HVAC controller to make this work, and I'll let Jens talk. But basically, there was both a valve to control flow and a variable speed pump to control flow, and I call it a cascade loop. He had a loop inside of a loop. Jens, well, I forgot what you call it, but the whole idea is they were able to make this work and to control the flow, so that, and because what the machine, because the compressor has no idea what the water's doing, all it knows is what the discharge pressure is on the refrigerant side, and so you just have to control to make that work. Okay. And yeah, so I think I said all that. And, so some observations about control. So at the system at Jackson that had the multi-pass system, there were 2 heat pumps. I showed one, but there were 2 heat pumps. And so the average, the first stage heat pump would run for about 20 to 40 minutes and then shut off. Sometimes the second stage heat pump would come on for a shorter cycle, and this shows you some of the variation. So it's cycling, the heat pump is cycling a lot in this configuration to meet the load. At Eastchester, everything's slowed way down, right? So it's pulling cold water out of the bottom of the first tank. It's pulling the hot water towards the beginning of the train. And so that takes a long time, and it takes 2 to 4 hours. And so at this site, we had like a week of data after the fact, and we found that mostly one heat pump could carry the load, except when there was a big draw, then the second heat pump would come on for a short time. So the M&V approach. So I came on site and I brought an ultrasonic flow meter, I brought a true power meter, and I basically, so there were already sensors inside the heat pump that told a lot of the story. I mostly used my sensors to verify those and make sure that it all made sense and the measurements were correct. So you see the ultrasonic flow meter hooked up to the pipe down below, and the control screen on the heat pump, which we got all the data off of. And of course, and I also had a very primitive handheld temperature probe that I could compare, I could insert and compare the sensors. And of course, so if I know the flow delta T on the ground loop side, the heat extraction, and I know the power, then I really know its heating capacity pretty close, and I can also find the COP. So that's what I did. And so summary of what we found for M&V, I was actually, so for the source flows, the Wilco pump actually reported a flow. And when a pump reports a flow, I'm always suspicious. But it turns out in this case, it was very good. It was very close to what I measure with ultrasonic. The fluid temperatures, we did see some variation from the controls, and we established some kind of offset corrections that we used. And power, so the water furnace unit actually reported power. It's kind of a surrogate measurement. It turns out it was very good, and I got, so everything, so really the only correction we did is the delta T we were getting from the system, we didn't 100% believe, so we did a correction on that. So at Jackson, the one that was kind of the multipass, you can see the first two columns, it's the load in and load out, so the delta T is about 10. It's coming back at 110, it's going out 123. And the saturated discharge on the machine, it was reporting that, it was about 130. The source temperatures for both these systems on this day was about 40. And and you can see my COPs, I get like an average COP of 3.5 in this case. And then on the bottom, so if you're in a multi-bass arrangement, the outlet water temperature is going to be slightly less than the saturated discharge pressure on the refrigeration system. And in this case, it was about 5 degrees less, which is normal, exactly what you would expect. So for Eastchester, we took the same data, and you can see the water comes in at 60, and it goes out at about 135. We actually tried various temperature set points to see how the system would work and get a curve at various points. But you see, and the average COPs were a little higher, it was about 4, but of course it depends on what you choose for a set point. And to state the obvious, if you ask for hotter water from a heat pump, it's less efficient. That's just a fact. And so you want the temperature to be high, but you don't want it to be too high. So we had experimented in this case. And down the bottom, so actually when you did this single pass arrangement with a high delta T, you can see that now the leaving water temperature is actually warmer than the saturated discharge temperature. And again, that's not a surprise because the refrigerant is superheated. You're basically going so slow that you're taking advantage of some of the hot gas from the compressor, and you get and you get water coming out higher than the saturated discharge temperature. So this is not a shock. And the Eastchester, here's kind of the Eastchester COPs at various leaving water temperatures. And we show, and so obviously as the water temperature goes down, we saw a little bit of a difference between 1 and 2. And I would say this is, the measurement uncertainty on something like this is 10 or 15%. And so I attribute most of the differences between these two as measurement uncertainty. So I think, so probably the true picture is in the middle. And here's just a picture of the longer term trends from Eastchester. We could get 9 days of data, and you can see, these plots show again the long cycles. The green is system one, system two rather, which is first stage. The red is system, the red system one, which is second stage. And you can see, you know, that the temperatures, the leaving water temperatures, you know, cycle as you go through, as it brings the system up to temperature and it satisfies the first tank. And you can see our average COPs in this case were about 3.9 to 4.1 across these days. So I got to thinking about this and I was realizing, so really, you know, so these units are controlled differently, but they're the same heat pump. So really, COP should boil down to the saturated discharge temperature. And so here is the two heat pumps at Eastchester. You probably can't see color, but these are the Eastchester heat pumps. This is me adding in the Jackson heat pump because it was operating at a different point. And like I said, because of measurement uncertainty, what I did is I said, you know, that line is sort of the best fit, sort of the average of what they all did at different operating temperatures. And what that did is, so that allowed me to, you know, so choose a leaving water temperature, because they all were operating at slightly different conditions. So to normalize it, I said, let's make them all operate at 135. If I know, if I have the leaving water temperature 135, I can back calculate what SDT is, because I was showing you that there's a 5-degree difference where SDT is higher there and SDT is actually lower there. And then I used that correlation I showed you, the best fit, and I could go through, and in the end, there's my difference kind of normalized for everything. So I got that just having a different arrangement with the same heat pumps saved us had a system COP that is 23% higher. So, you know, so I just, you know, so hot water systems, it really depends on how you arrange the system, what the flows are. And this is, you know, so I was old enough to be working in the solar industry in the 1980s. All this happened then too, right? Because a solar collector efficiency is high if you jam a lot of water through it, but the system efficiency is higher if you have lower flows, more tank stratification. And when I say solar, I'm sorry, the solar hot water industry. It used to be called just the solar industry, but then PV stole the show, and everybody forgot about solar hot water heating. But this was sort of an issue with solar water heating in the old days, and the same kind of rules applied. And so one thing about the savings is, so the way we've done this, I'm just focused on the heat pumps. When I've looked at other sites, I've seen that going to this lower flow arrangement, actually there's tremendous savings from just lower flow and less recirculation losses and all that in the tank that I'm not even measuring. And at other sites, you know, so at other sites, I've seen that to be 10 or 20%. So kind of to go through it, you know, so the series arrangement makes a big deal on heat pump performance, and it makes the same heat pump work a lot better. And, you know, so you need to put them in series and have lower flows. And the hard thing is you can, and we showed that we could take a unit that wasn't even meant to be single pass, and with the right controls, you can make it perform like a single pass system. And you end up with leaving water temperatures that are even higher than your saturated discharge. That's wrote in 23% savings just on a snapshot. And like I said in the last bullet, so at Zero Place, another building I monitored with Jens, we actually had very detailed measurements on the recirculation loop, and we can measure thermal losses. And small changes in the recirculation loop and all the mixing of the tank have tremendous impact. And I think that there's probably, that if we could measure total use here and everything, that probably another 10 or 20% can be, savings are actually happening, but I did not even catch that with what I measured. But it's likely that there was some impact of that. So you want to just jump into yours?
I I will jump in.
Or should I take questions?
Well, maybe we do them at the end.
Okay.
Yeah.
Sure.
Perfect. There we go. Like I said, yes, my name is Jens Ponikau. I'm the president of NY-GEO here, and I'm also the principal of Buffalo Geothermal. So we had the pleasure to get involved in this project. And there was kind of a funny story because I was sitting in Albany with the predecessor from Rory Christensen here, and I was yelled at like crazy because right at the Public Service Commission, you being here is a total waste of time. Ooh, what did I do wrong? Well, this was the time when Con Edison was declaring a moratorium in Westchester, and they were not connecting any new customers to gas anymore. And he, as a chair, had his earful all morning from developers, from the government, from everybody else, and those were a little blank. So he said, you should be here and just go down to New York City and show them how to do GEO. Never done that before. So it goes that actually J.J. Rodriguez came and from CSA and called me that evening, totally unconnected, and said, Jens, have you ever done a project in New York City? It's like, huh, funny you ask. I said, so where's the building at? Plural buildings. I'm like, okay, how many? Well, 7 of them. Uh-huh. How big are they? Well, 17 stories each, and we want to do only hot water. I said, well, first of all, nobody's ever done that there before in a retrofit, and then, oh, by the way, hot water, we're putting heat out 24/7. I don't think it's going to work. I mean, I'm going to run the numbers. So where's the development? See, plural again. There are 2. So it's actually 17 buildings. And I said, well, are they empty? No, they're going to be occupied with about 4,000, 5,000 affordable housing tenants. So I'm like, sure. I said, let me run some numbers, I'll get back to you. So this is how this all started. And it's kind of a funny story on how this evolved. So this is Jackson, just to give you an idea about, I called it the biggest shacking in the world, New York City, for construction. So we got involved in it, and we designed the system for them. And this was the specifications. NY-GEO said you have to come up with a COP over 1.8. Only then can we meet our mandatory emission reductions while we're actually doing this. And they had selected a heat pump, a Colmac, which had a rated efficiency under those conditions of 130 degree output, 140 degree output of a 1.8. So, and we said, well, I think we can beat this. We just have to look at the different equipment. So I actually called Water Furnace, and we kind of all hooked up there. And we talked about possibilities, what kind of machines we were able to use, how they need to be designed, etc., and whether they would consider doing an engineering special for us. So this is Paul Selking, the VP for commercial business, and this is Marek Zekovic. He is the supervisor from Adams European Contracting, who actually was the GC on this project. So we were trying to figure out on where can we find and build machines which can actually do what we're trying to do. Then this is, I always call it the prototype at Water Furnace here in their development lab. And this is a double wall heat exchanger, a plated one, which makes sure that in case of a refrigerant leak, the leak doesn't get immediately into the potable water, because this is potable water now you're heating, correct? So actually, the unit they came up with had a COP of 2.2, giving the high efficiency of the heat exchangers, and this was a liquid injection prototype. And they were able to increase the COP by about 23% roughly. So we were pretty happy and excited about it. That was me actually on the assembly line there, so I wanted to understand on how they work, and they were so gracious to welcome me there. And talking about the ins and outs about the units was actually pretty neat. Here is where the liquid injection compressors were assembled into. These were the heat exchangers coming from the suppliers. So that was all pretty cool to see all that on how this actually was happening. So you see here now this unit running at, with about a 10-degree delta T, which we usually have, and this is pretty normal, right? And this is where the limit is pretty close. 130-degree output, 140-degree output roughly, and the pressures are pretty high, and the kilowatts that the unit is using is pretty high. And then when we had this all assembled there in that way, then we said, oh, why don't we slow it down and make the water hotter in one pass-through? So we started to do this. And you can see it's about 40 degree coming in. It's about 150, 53 going out. Wow! Every engineer would get a heart attack. So did we. But look at this here. How is the discharge pressure? 450? How is the power usage? It's down. Isn't that odd? You make an unprecedented lift, and now suddenly the performance goes up. We were a little baffled, to be honest. So what we did is, you see here the jump in this efficiency, and this is when we put it into this very aggressive slow mode range. And this is a very small screen here, by the way. So this is when we kind of slowed it down a little bit. We didn't put 137 degrees out. We've experimented a little bit once we had that stable. And that was kind of the neat way to have this operating under very stable conditions that way. And then we said, okay, what is the potential of this? Where could we theoretically push this? Because apparently this heat pump does not know what it's doing, because it doesn't know it's making 164 degree water. It's operating like it's doing 110 degree water. It was very odd. So we started to slow down further and said, what's happening? So where do you think this is going? What do you think is the limit? What is usually the hot water we can make with heat pumps? Any idea? 120, 130? That's where we're usually going with. So, well, what is this? 180? What are my pressures doing? 580? So the high pressure, this is rated until 650 as a high pressure cutout here. So this heat pump is humming. Nothing else is happening. So what's the potential? So we are where? 186? Pretty hot, huh? The heat pump is healthy. It doesn't know it's making 186 degrees. So 190. Again, this is under very controlled settings. We were able to control this up to a degree. And we controlled very straight the kind of water going in and what the exact temperature was. But how's my heat pump doing? Not too bad, about not even 600. You want more? Well, we're getting up there slowly but steadily. And then the question becomes, you know, I suddenly had to think about this movie. I want the truth. You can't handle the truth. Well, is this a new threshold? And how's my pressure doing? Well, about roughly 40 psi below the pressure limit. Well, we stopped then because we didn't obviously want to damage anything, but there is a huge potential here. But what I'm telling you, I'm playing a little bit of a game here with you, is that is not the goal. That is for bragging rights. That's not the whole purpose. Because now think about it, if you now put it in a normal 140-degree motors, you get a reward. And that is an unprecedented efficiency we're suddenly having. And once we realized that the key aspect is that we are flushing this heat exchange on the load side with cold water, we said maybe we're going to store cold water in order to make more efficiently hot water. Isn't that odd? But this is how the physics work. And quite honestly, it took us a while to figure out how this would all work. But what you see now is that we're using part of the system as cold water storage in order to let this heat pump run under more favorable conditions. And that's what it's doing here. So we let the tank build up. We don't turn the heat pump new on to remake this hot water. We use the first tank as a cold water storage tank. And the heat pump starts going on. It sends the hot water to the building. But when the building doesn't need as much hot water, it fills up the tanks backwards from top down and pushes out this cold water again. But you can let it run now under scenarios like that, sometimes for 12, 15, 18, all day under those extremely favorable conditions. Because we have a second heat pump as a second stage. So the first stage runs sometimes 24/7 in a multifamily setting like this. And we realized that the efficiency can be further maximized after we started to play around with this a little bit more. Hugh was measuring this when we weren't at the last stage yet, where we were actually controlling this much better and dealing with this cold water storage. And so the efficiency suddenly went up even further. Now think about it. It took us 10 years to increase the efficiency by maybe 10% on a regular heat pump, a little bit larger heat exchanger, a little bit more here, a little bit more there. But for us, those things were quantum leaps. So now this is with 410A, have that in mind. Now we have the new refrigerants, which seems to be even more favorable in heating. And we also integrated this now into newer buildings where the water temperature is not 30, 35 degrees coming in, but it is actually heating and cooling being injected into the loop. So our average water temperature is 50 degrees, in the summertime it goes up to 70, 80, and we see unprecedented efficiencies which are not even counted here. So this was then, this is Amanda Schneck here from Water Furnace, this is Marek again. This is how they actually look at NY-GEO when they are installed, 2 of them, and they are kind of running in kind of a lead-lag configuration. But as you said, this is only half the story. Because now, if you have the whole system designed to pump 120 gallons through the source loop, but now you're only using one heat pump, and you're only using 60 gallons, your pumping power can go way down. And this is for the source. This is then the next part of the story. So we're pumping approximately, you gotta look here again, 57, roughly 60 gallons a minute here for one heat pump on the source side. And what is my pumping power? That is the second one from the bottom up. So we slow down the pump so much that we are only pumping 60 GPM, and my pumping power instantaneously is 0.18 horsepower. That is about 140 watts, 130 watts to pump 60 GPM. Compare that with a 20 horsepower pump sometimes sitting there. This is 120 watts. It's a little bit more than a light bulb, a conventional one. What about on the load side? If I now slow down the load pumps, which circulate all that water normally through the heat pumps, where can I slow that in? Well, first of all, we realized that the trick is when you start to flush this unit with ice cold water, it can transfer a huge amount of heat it pulls out of the refrigerant circuit. And if you compare this, keep in mind that unit is rated at 170,000 BTUs. It's a 30-ton normally. 170,000 BTU heat extraction on the source side. When we run it that way, we measured 394,000. More than double as much. of heat extracted. So this unit runs like a 50 to 60 ton unit under those conditions in terms of performance. Secondly, the power consumption went down instantaneously. The compressor power was decreased as a result. What does it do? Lesser electric consumption and more heat extraction. COP. That's where it's coming from. It is really a huge amount of heat extraction we're looking at. And the capacity for this unit is up by about 63% in total. But the trick is that the energy actually comes from a much higher heat extraction. So, I mentioned load pumping power. So these are our load pumps for each one of the normally 60-ton unit, 30-ton unit, but it runs like a 50-ton. This is 44 watts on the load side because I'm only pumping 15 GPM through a heat exchanger which is designed for 80. And where can you push even that? We were kind of joking around and saying, that sounds pretty high. Can we get this lower? Yeah, we can get this lower by playing around with it a little bit more and slowing the water even further down. How low can you get this? This is not 200 watts, this is 2 watts pumping power for a 30-ton unit. That's what Hugh was referring to. All the auxiliary system equipment can be on a whole new level. The problem is you can't just put a very tiny little small pump in there because when this water when the tanks gets replenished and the water temperature goes up, and now suddenly you're not flushing this unit with 40, 50 degree water, but you're flushing it with suddenly 70, 80, 90, 10, 110, 130 going up, then this pump needs to do 2 horsepower on pretty much an instant, and you need to control that. That is the trick. Everything is good as long as the water going into this unit is cold. Here's the reward. Remember when this was going up and down like crazy, when the unit was turning on and turning off and everything else? This is where it's running for 24 hours. Because we always have a minimum of hot water consumption, and then we have a maximum of hot water consumption. But you can nicely see here, we're pretty much around 140 degrees for the last 24 hours. This is then going into a mixing valve, and the mixing valve is mixing this down. And we send out about 120 degrees there, 125 degrees to the building roughly. And, but you can see how flat this line is if you know how to control it. And you control the water flow. Again, this was the result, what we finally ended up with all the accessories there, if you count it in. And yeah, this has been recognized. I just mentioned, or I actually met somebody here from ENR, Engineers News Report. This was chosen to be not one category, but 2 categories now, and for multifamily and best category for sustainability for the region here, for the East Coast, for New York City and Boston, etc. So this is one of the top-rated engineers project now, and we just got news that we actually, what I didn't know, I didn't anticipate that this was forwarded to the national competition where all the best regionals were actually put together, and it beat them pretty much all out. They had 200 submissions in the sustainability category from the who is who in the country, and this won the best project, best of the best, nationwide. Because we were very convinced that this will be transformative in our sector. This will be the way how hot water will be made in the future. There's no doubt in our mind. And I want to thank specifically Adams European Contracting and CSA who hired me for this project. We have Mark Preston and Merrick Zakovich here, the project manager and the supervisor for that. They were the 2 best guys to work with. I've never had so much fun in my life on a project. And I want to thank NY-GEO, who allowed us to innovate and said, hey, test 2 of them, and come up with the best solution. And that's what we're allowed to do. And this blew pretty much everything else we looked at and tested up out of the window. I want to thank Water Furnace for going those innovative steps in building a unit we were seeking for that. Not understanding how far the story can go, you know, we were happy to have 20% better heat transfer and better efficiency. And Amanda, I think here too, she was a Water Furnace rep, also deeply involved in this, and she was on one of the pictures there. Actually, that's her here with Merrick, checking the units out. So, what I also didn't know, and I don't want to brag about it, but it's kind of a funny story. There are 2 competing societies here, or entities here. One is ENR. They have a 25-person jury for this. The other one is the ACEC, the American Council for Engineering Companies. And it actually, this project won the highest tier, the Diamond Award in New York City as an engineering project. What I didn't even know either, that this was also forwarded from their regional societies to their national societies, and it won the Grand Award from them as well. So we are going to Washington, D.C. in May, I believe. So again, I couldn't have done it with so many people here. And it was a pleasure, but here's a reward. So, any questions? Yes, please.
Rick Clemenzi, Geothermal Design Center. First of all, congratulations, because this is an idea I had years ago and spec'd out on a job, never happened. And it's bravo. But you went really way beyond what I thought. The whole cycle with the tanks and all that, I really had that. But I wanted to say, so is it my understanding of what you just said, that if we just put oversized heat exchangers in all these systems, we're going to get like performance beyond what anybody's really ever put on the table, and maybe we just need to be rethinking this small piece of the capital cost up front in the equipment on the size of the exchangers versus the long-term gains on efficiency, and maybe that's an extrapolatable learning from this?
Well, the heat exchangers has not changed inside the unit, they're the same. We are just creating a larger delta T, and because of that, we're pulling more heat out of the refrigerant circuit.
Okay.
The size of the heat exchanger and the size of the unit has changed, just performs twice the heat extraction and lower power consumption overall.
Yeah, I think, you know, so the heat exchanger actually, when they have low flow, the refrigerant to water heat exchangers are less efficient, but I don't care about that efficiency, I care about the system efficiency. So there might be small penalties in the efficiency of the heat pump, but I don't care about the heat pump, I care about the system, right? So so I think the proper view is to look at the bigger picture.
Yeah, the Ponikau went down because we slowed the flow down from an unusual amount. Where this heat exchanger, obviously, it's designed for a much higher flow, but you need this flow at the very end when you don't have cold water anymore, when you're running out of cold water storage, and now the hot tanks are sending fluid back to the heat pump, and now we better wrap up this flow very quickly within fractions of a second. To make sure that the pumps are actually reacting to that. I mean, we're working with 4 PID controls here on this to control all of this. It's not an easy task. We decided to bring controls in-house for that. But it's obviously, you saw the curves. You have a flat curve. And it's working extremely well and extremely stable. And like I said, for us, the next frontier will be what this unit can do and what we can do with this kind of range design and control design. And now, not when the ground alters at 35 degrees, what it is there, because we're taking heat out 24/7, 365. But what happens when we're actually putting heat in
I got I got a comment for him and then a question for you. You had a good question, which is if you increase the size of the heat exchanger at the narrow delta T flow rates, will it increase the efficiency similar to what you saw? And the answer is yes. For a company that manufactures high temperature heat pumps, I'm up talking next, that is a fact. So good question. My name is Chris Evener. I work for Now Water Heating Systems. Sorry about that. Question to you all. Doing what I do, where do the discharge pressures and suction pressures that you measured fall on the compressor map for these particular compressors? Because we see this all the time, that especially 410A can be pushed very far, but the sacrifice is how long the equipment lasts.
Yeah, I mean, keep in mind, we showed you one very snapshot where we wanted to see how high we can push the heat pump in terms of discharge water temperatures, but we're running this at 140 degrees normally. And then the pressures are around 350 psi, as you've seen. So it's actually, I think it's going to be beneficial for the heat pump because it uses much lesser pressure and much lesser gas temperature than under normal conditions. I showed you the two different ones when you have high flow and what we call low flow, high lift. And the high lift was suddenly, the heat pump was not knowing what it was, that was making 140 degrees. I think the heat pump will be is under much lesser stress operating it that way than the other way around, than the conventional way.
Yeah, so what we showed, so for the single pass arrangement, our highest saturated discharge temperature was about 130. And so, it's 454B, this 454B. And so, yes, so I think that's well within the operating, oh, this was 410, okay. But I think it was inside so let's say the good operating map of the compressor.
Yes.
No.
Yes.
Hi there, Matt Damaris from Energy Catalyst. First of all, really good project. Congratulations, Jens. I just wanted to clarify, I have two little clarifying questions. My understanding of what you're saying is that because of the high lift, it's not necessarily high lift in the traditional sense, but the water temperature comes in very low and then it's being raised high, but you kind of need that in order to get the high efficiency, right? So for instance, if your water temperature came in at 100 degrees, you would actually potentially get lower efficiency. And then what you've designed in turn is basically a plumbing arrangement that helps to keep the system in that optimal position at all times. Is that a fair summary of what we have? Would you mind just explaining, is that? Oh,
I'm glad we got it over.
Yeah.
We'll try to hammer this way home, yes, but that's really
You can quote me on that for summary purposes, yeah. So would you mind just sharing one more time, now that I understand that a little bit better, just going back to the diagram that you had revised, I just want to understand under which conditions would because you have that buffer tank, the hot water buffer tank, and it's the hot water and the cold water. I just want to understand under what conditions would it go. Does it ever go backwards, I guess is my question. Does it go forward in one direction in certain conditions and then backwards in other conditions?
Yes. So it depends on how much the building is using. If this is, so here's, let's say, a 30-ton unit that makes 30 tons of water. And, but we slow down so much that it makes about 15. You kind of got my question. Roughly. And then it goes through this, mixing tank. This is actually an electric tank, which is kind of disengaged or run at a very low setting, so it doesn't come on under normal conditions unless we have an emergency or a failure or something like that. And it goes through here, and then it goes out to the building. So if now the water draw from the building is more than the heat pump can make, then the water automatically comes from the buffer tanks flowing in this direction. Because here's a cold water supply, it goes in here and pushes the hot water out, and then adds to the hot water production here. In reality, we have a second heat pump there coming in as phase 2, so for the peak times. But if this is now going lower than what the heat pump can make, the heat pump still keeps going, and down, and because the hot water is lighter, it stays up there and pushes down the cold water out of the tanks in the opposite direction. So it's a little confusing because a lot of times we're going in and out of the tank with the same pipe. And there are flow reverses depending on how much the building is using. But that ensures that we have this very cold water stored and we don't disturb the stratification, which we think is extremely important. So that's your surge management. Yeah.
Yeah, and another way to answer the question is I think that, so when there's a draw, water is going the expected way, right? It goes from the low, it goes from 1, 2, 3, but when the heat pump is heating the tank, it goes backwards. It goes 3, 2, 1. So the flow is backwards when it's just a heat pump. It's forwards when there's a draw. And when both are happening, it depends on, it depends.
Yeah. Okay, there were other questions. Yes, please. The next. Yes.
I'm coming. No problem.
Steve Martino, CDM Smith. Phenomenal project. Super interesting. I really like it. Thanks so much. Is there a way to equate this type of system to domestic heating, like for baseboard heating in a residential home? Because 180 is perfect, right, for the baseboard heat, I know, but this seems like it's totally different arrangement. Have you guys given that any thought of how you might accomplish that for?
We don't see that, at least with this kind of design. And I'm also not, I admit, I'm not designing heat pumps. We're designing geosystems in that way, so I would refer that to the manufacturers if that's possible. The answer is, in my opinion, no, because it depends on that you flush the low heat exchanger with extremely cold water. And your return water from the heating system is maybe 10 degrees less, but that's it. So that's really the I shouldn't say downside, because for us, the hot water was always, we can heat a building nowadays, which is even retrofits with some insulation with 120 degree supply temperatures. Or we add a few radiators, or we add fan costs, we can figure this out. There was always the holy grail here. How do I make it hot water, cold water, and have that? So, again, good question, but that's the first thing which I was like, hey, can we use that instead of steam and use the same radiators we have there and just get the, no. So, unfortunately. Yeah, understood. I mean, not a question. Where's the efficiency then if you are running at that high? Okay.
Lower, of course.
Yeah.
The pump is the same, but the first model of propane is much higher.
Okay. Appreciate it. Thanks. You were from Echo Force, right?
Yeah.
Very good. Just say your name again, we need it for the videos.
But
Harpo from Echo Force. Very good.
in Europe, we are using propane,
Yeah.
and the first mod in extreme condition is much higher.
Yeah.
So in winter, to reach higher temperature, extreme outside temperatures, we require, of course, require the same. But we can use the gases and replace boiler.
Understood. What you're saying, I mean, we understand the issue. Europe uses propane now as a refrigerant with a.
From 410 propane therapy.
Correct.
Here, we are from 410.
Yeah, it was certainly a fire issue or flammable issue, or what people are afraid, not necessarily reasonably afraid, what I'm trying to say. And there's something maybe we really need to have a discussion here in this country, or maybe in New York State, to say we need to change the regulations to be permitted to do that.
Say last question.
Say your name.
Again, I'm not an expert in refrigerant circuits, but that one I got. So yes, Europe is much more ahead, and also their global warming potential is obviously almost nothing with propane, so that we would solve a lot of problems with that. There was another question back there. Yes. We're here outside the room for you with the questions. Thank you. Sorry about it. We have to stop it. Thank you all for coming. It was a pleasure. Oh.
It's been happening all day. It's been really irritating. The crew over there stepped on the thing, so that was easy. How's the ground feel? Floor feel?
So it's running, it was about 40 today, I was measuring. And so it is clearly imbalanced, right? If you suck heat out of it all year
It'll
round,
only ever.
go down. Well, but no, it doesn't. You know, this concept that loops have to be balanced.
No.
Yeah.
But it'll eventually,
Season.
over 30 years,
It might
it'll
go
get
down.
cold.
Yeah.
There's
Well,
spaced
actually,
enough.
Yeah, so I don't know how the long
He
term.
modeled it then.
Yeah,
the
he
Geo
modeled
loop
it.
or whatever.
So I would think he